Hello and welcome to this exercise on curves and tangents. It is an iGCSE additional mathematics question and it's quite involved. There are 6 parts to this question and there's everything in here. Think of every skill we require for in mathematics, really. So there you are. Hopefully you pick and choose where you want to come in, and it's exactly up to you what you do. And there are 18 marks in here, so there's something in here for everybody, hopefully. Okay, now for the next slide. Well, okay, now this is the first part of 6 for the question itself. And you know the curve C has the equation y is equal to x to the power 4 is equal to 4 to 4x to the power x cubed minus 2x squared plus 13x plus 5. And line L sub 1 is tangent to C at the point R where I has the coordinates 113. And it says find an equation for L1, which is a tangent at R. Now I think because of the amount of work, amount of the the, the value of this question, 18 marks in total, it wouldn't be a bad idea to use your graphic calculator to sketch out the curve, and hopefully she has something like this. It does help. So we got the equation y is equal to x to the power 4 minus 4x cubed minus 2x squared plus 13x plus 5. Now, because this is a tangent, we need to find the gradient. So if we then do dy dx, we end up with 4x cubed minus 2x squared minus 4x plus 13. And because this tangent touches a point R, and R has got the coordinate 113, if we then substitute 1 to dy dx to help us find the gradient of L1, we end up with L1 being, so we end up the gradient being 1. So because we got 4 minus 12 minus 4 plus 13 gives us 1. So the gradient of L1 is 1. Now to find the equation of L1, we then do y minus 13 divided by x minus 1 is equal to 1. When you simplify, you end up with y minus 13 is equal to x minus 1, or if you like, y is equal to x plus 12, or if you wish, y minus x minus 12 is equal to 0. So that's the first part done. And L1 is going to be this here. So that's your L1 there. Hope that makes some sense. Right, next slide. Now, this is for part B, and I think part B is the most difficult of the 6 parts, I think, because there's a lot of exploration involved. Right, it says the points P and Q lie on C, the s-coordinates of P and Q are subcase P and subcase Q, respectively. And it says we are lowercase p is less than lowercase q. And it said the tangents to C at P and to C at Q are parallel to L sub 1. Okay, right. That means that the derivative from the first equation we had in part A will be equal to 1. So that's okay. So let's find the coordinates of P and the coordinates of Q. Right. As I said earlier, the derivative for um, the tangents at P and the tangents at Q will be 1 because they're parallel to L sub 1. And from part A, we found dy dx, which was 4x cubed minus 12x squared minus 4x plus 13. So that was dy dx from part A. So if dy dx is 1, this must also be equal to 1. And then if we subtract 1 from both sides, we end up with 4x cubed minus 12x squared minus 4x plus 12 is equal to 0. We can isolate 4 because 4 is a factor of 4, 12, 4 and 12 again. We can isolate 4 and we end up with s cubed minus 3x squared minus x plus 3. And then we can, if we divide both sides by 4, we end up with s cubed minus 3x squared minus x plus 3 is equal to 0. Now, how do we factorize this one here? Well, we know that this expression also applies to the point r. Okay, and at r, the x value is 1. So it's then possible that x minus 1 is going to be a factor of x cubed minus 3x squared minus x plus 3. Now, to check if you're right, if x minus 1 is a factor, then x is equal to 1. And if you then substitute 1 into the derivative we've got there, so now we end up with 1 minus 3 minus 1 plus 3. That gives us 0. So x, by the factor theorem, x minus 1 must be a factor. Okay, so if x minus 1 is a factor, if we then try and do this, if we then do either by synthetic division or by long division to get the other factors of this expression, we then get x minus 1 into x squared minus 2x minus 3. And to make life easier, make that simpler, I've got x minus 1 into x squared plus x minus 3x minus 3. All I've done here is to break up my minus 2x. So if I don't factorize this group here, this little x squared plus x, I get x into x plus 1. Similarly, if I factorize this little bit here of 3x minus 3, I get minus 3 into x plus 1. Now both groups have got x plus 1 in common. So when I then combine, I end up with x minus 1 into x plus 1 into x minus 3 is equal to 0. Now we know that this x minus 1 refers to the point at R. So this x plus 1 and x minus 3 must refer to the points at P and Q. Now if x plus 1 is equal to 0, then x is equal to minus 1. And if x minus 3 is equal to 0, then x is equal to 3. And that's what it goes there. But we know from there that lowercase p is less than lowercase q. That's the x values at p and q respectively. So it then follows that x equal to minus 1 will refer to lowercase p, and x equal to 3 will refer to lowercase q. Okay, that's the x coordinate at the point q. Okay, if x is equal to minus 1, and substituting, we're going to have y is equal to minus 5. And if x is equal to 3, and by substituting, we get that y is equal to minus 1. So the coordinates at P and Q will be minus 1, minus 5 for P, and 3, minus 1 for Q. Right. I'm going to do something not required in the equation itself. I'm going to try and find the equation of the tangent at P and the equation for the tangent at Q. Now, if the gradient of the tangent at P is 1, okay, and we know the coordinates of P, which is minus 1 and minus 5, we can find the equation of the tangent at P, and that gives us y is equal to x minus 4. Similarly, if the gradient of the tangent at Q is 1, and we know the coordinates of the tangent at Q as 3 and minus 1, we can also find the equation of the tangent at Q, and that turns out to be y is equal to x minus 4. So the tangents at P and the tangents at Q have got the same equation and got the same gradient, so they must be collinear. Okay, so I just preempted what's in part C. Anyway, this is what we got here. This line here is the original L sub 1 line, and this point here is R. That's R there. And this line here is the line that joins P and Q there. And it's L sub 2. It has to be L sub 2 there. Okay? So P and Q are collinear there. Anyway, moving on. I just preempted part C there. Right, and part C said the line L2 passes through P and Q, find an equation for L2. Now, clearly L2 has to be y is equal to x minus 4, as we found out from this discussion here. Anyway, moving on. What I've done from part B, P and Q are collinear, so we've done that anyway. Moving on from that, we can actually find the gradient of L sub 2 by looking at the coordinates of P and the coordinates of Q there. So we can do that. And if you look at this, if you look at -5 minus -1, that would be the y's. The -5 comes from the y value of P, and -1 comes from the y value of Q there. And from that, you can get your gradient for L sub 2, which has a gradient of 1, which confirms what you said earlier there. Okay, so in effect, the line L sub 2 has got the equation y is equal to x minus 4, and it's parallel to L sub 1, as you can see from our diagram on the right hand side. Okay, moving on. For part D, you show that L2 is tangent to C at Q. Right. We've shown that L2, as we have known, is a tangent at P and Q. So L2 is tangent at P and also a tangent at Q there, because it's got the same gradient as the tangent at Q originally, and the same gradient the same gradient as the tangent at P. So L2 is a tangent at Q. Okay, and I hope all that made some sense. Moving on to the next slide. Right, okay, now for parts E and F, or part E first. It says the normal to C at R, where R has got coordinates 113, intersects L2 at the point S. Don't forget L2 is the line from P to Q. And then it says find the exact length of RS. Okay, where RS is now the normal. Right. The normal at R, that's got a gradient of -1, because we know that the product of the gradients of the tangent and the normal is -1. And if in this case the gradient of the tangent is 1 at R, it then follows that the gradient of the normal at R has got to be -1. So the gradient of the normal at R is -1. So that being the case, we can now try and find an equation for the normal RS. And to do that, we do y minus 13 divided by x minus 1, where 13 is the y coordinate of y coordinate at the point R, and 1 is the x coordinate at the point R. So y minus 13 over x minus 1 is equal to -1, and we then end up with y minus 13 is equal to 1 minus x, or minus x plus 1. If we then add 13 to both sides, we end up with y is equal to 14 minus x. Now we need to equate the y values of both the normal and the line L sub 2. So we then have 14 minus x is equal to x minus 4. Okay. And when we try and simplify, we end up with 2x is equal to 18, which gives x is equal to 9. And if x is equal to 9, then y is equal to 5. So the normal will meet the line L sub 2 at the point S, where S has got the coordinates 9, 5. Okay. Now, having found the coordinates or at the point S, we know the coordinates at the point R. We can then use Pythagoras to find the length of the line RS. Okay. Now, using the x coordinates for both S and R, and the y coordinates at both S and R, we end up with s squared plus s squared, which is root 64 times 2 there. And the square root of 64 is 8. And because they want the exact length of RS, our answer will then be the length of RS is 8 root 2. Okay, and now for part F, and it says find the area of the triangle PQR. Right, to find the area of the triangle PQR, we need to find the height of the triangle, in this case 8 root 2. So we know the height is 8 root 2. We now want to find the length of the base of the triangle, in this case the length from P to Q. And we know the coordinates at the point P and the coordinates at the point Q. Okay, so we can now use Pythagoras to find the length of PQ, which is now the base. Okay, so now if we now use the x and y coordinates, so that will be the y coordinates, that will be the x coordinates, that will be the s coordinates, okay, for P and Q. So we end up with 16 plus 16 there. So we've got two 16s. So that becomes the square root of 2 times 16. And the square root of 16 is 4. So the length of PQ is 4 root 2 there. And we know the height, and we know the base. We can now find the area of the triangle, which is height times base divided by 2. And 4 root 2 times 8 root 2 will give us 32 times 2 divided by 2, and the answer is 32 units squared. And that's our answer. Now, I hope all that made some sense, and thank you for watching. Please subscribe, and hopefully see you again sometime.